Okay, so this is question 6 of assignment 1, and um, in this exercise, they are basically asking us to prove that the cardinality of the positive rational numbers is the same as the cardinality of the set of natural numbers, and we're using this theorem that they've given us without proof uh, to prove this fact. Um, and this theorem basically says that if if q, the rational number, is also a natural number and it's not equal to 1, it is given by this equation here, where p are p1, p2, all the way to pn are unique prime numbers, and r1 to rn are exponents. And if q is not a natural number, which means it's a proper rational number, it's given by this equation instead. And then we're given this function f here that maps the positive rational numbers to natural numbers. And in part A, we are asked to compute what f of 4 over 15 is. Okay, so we'll start with that. Same thing. The definition of f is so that if q is a rational number but also a natural number, it's given by this. If it's just a rational number and it's not a natural number, it's given by this equation. And since 4 over 15 is a rational number, we would use the second equation here, right? So in order to use the second equation, we would have to get the exponents and the prime numbers of q, and we can do that by first factoring it into its prime numbers, which is given by this. Then we can sub that into the function f to get so p1 here is one prime number in the numerator and two prime numbers in the denominator. So it's p1 and then it's q1 to s1 minus q1 to s1 minus 1, q2 to s2 minus 2, right? And we just sub those in, we get 2 to the power 2 to the power 2 times 2 times first prime number of the denominator, and that's just 1, so we get 2 minus 1, that's just 1, and same thing for q2, it's just 1, and in the end we get 2 to the power 4, which is 32, 16 times 3, that's 48, times 5, which is 240, right? Yeah. Now it wants us to find q such that f of q is 108. So we're given that f of q is 108, but we don't know if f of q when it's mapped back to q, if it's a rational number and also a natural number, or if it's just a rational number, right? If it's just a proper rational number, or it's uh, um, a natural number as well. So we'd have to test out for both cases. In case one, we assume that it's a q that is a natural number also. And so let's just q equals to p1. Oh, I think before that we have to factorize 108 into its prime numbers. So we can do that here. 2, 5 very quickly. 2, 2 4, 1, 7. Be 2 to the power of 2 times 3 to the power of 3. Right? So f of q might be given by this or this. And so we have to test it out for both cases. In the case that it's the first one, f of q would be thus q cannot be a natural number because r of 2 has to be a natural number, right? So this gets mapped to this, and the exponents r has to be a natural number. So it can't be case 1, so it has to be case 2, where q is not a natural number. So fq will be given by this. So the second prime number can't is shown previously that it can't be in the denominator. Sorry, it can't be a value of p, so it has to be a value of q here. right? And so now that we know R1, which is 1, and S1, which is 2, and we know that Q cannot be a natural number, so it has to be given by this equation. And if we do that, we will have P1 here, and 1, and P1, sorry, Q1, S1, P is 2, R1 is 1, Q1 is 3, and S1 is 2. So Q is 2, 9, and we can just check that this is correct by mapping it back to f of Q. We do this, and f of Q is given by that, where P1 is 2 of R1, and Q1 is 2 of S1 minus 1. We get 2 times 2, sorry, 2 times 1, Q1 is 3, 2 times 2, 4, 3, that gives us 4 times 27, and sure enough, it maps back to 108. So we found our answer Q. Alright, so moving on to part B. Now we will use the theorem to prove that F is a bijection, therefore proving that the cardinality of the rational numbers, positive rational numbers, is equal to the cardinality of the natural numbers, right? So how do we prove that F is a bijection? We want to prove that F is an injection and a surjection. Injection meaning it's one-to-one, and surjection meaning it's onto. Right? So we know from the theorem that for all P1, P2, Pi, theorem says that all Pi in the natural number case it P all P's are unique. So Q equals P1, P2, R1, R2, Pi, Ri, And if they are unique, that means that f of q which is given by this in, again, the natural number case, is also unique. So then we've proven that f is 1 to 1. So f is 1 to 1 for q in the set of natural numbers minus 1, right? Same reasoning for q for all elements of rational numbers that are not natural numbers. Q given by this implies that fq also unique. F is 101 for q for all q so for q equals to 1, q equals to the natural number, q equals to the q being an element of the set of natural numbers besides 1, and q being the proper natural numbers, all 1 to 1. Thus, f is an injection. So we've proved that f is an injection. This is part 1. And in part 2, we want to prove that f is a surjection. So we first let M to be an element in the set of f of q, right? Where q is in a set of rational numbers and they are positive. Then there exists a value Q such that f of Q equals to M, right? So then M, any arbitrary value in f of Q, is mapped by the function f, then there would exist some value Q such that f of Q would equal to M. Thus, f is also surjective. Finally, f is a bijection.